So solid state devices are an integral part of integrated circuits, and this notion of integrated circuits has been introduced by Sir Jack Kilby, who was working at Texas Instruments with the dream of building a monolithic integrated circuit. So the first integrated circuit that was developed by Kilby in the year 1959 was basically connecting two p-n junction diodes with the help of resistors that are connected externally, as you can see from this picture. In 1961, TI and Fairchild introduced the first logic ICs, and the first MOS transistor was developed by RCA in 1962. You can see the pictures. So since then, integrated circuits have worked a long way, starting from a flip-flop with two transistors to Intel Pentium 4, consisting of 55 million transistors in 2003, sitting on the same size of the IC. The size of the memory has also increased dramatically across the years, with 0.5 billion transistors in a 512 megabit dynamic RAM. So there was a 53% compound annual growth over 45 years, and that is basically driven by the miniaturization of transistors. Smaller is cheaper, faster is faster, and also lower in power dissipation. And this has created a revolutionary effect on the society. So starting with those simple microprocessors of 70s and 80s, we have walked a long way with the microprocessors of today, with Pentium dual core processor, Pentium quad core processors, and so on. So across the years, the area of the chip has remained the same, but we went on putting more and more devices on the same area of the chip, and that's how integration has come up across the years, along with increase in speed, reduction in power dissipation, and reduction in cost also. So the driving force behind all this integration has been the Moore's law. Moore envisioned way back in 1971 that the number of devices that can be integrated on the same area of the chip will double every 18 months, and this trend will go on in near future. And curiously enough, 40 years after his elicitation, we are still seeing the same trend with respect to the level of integration on the semiconductor ICs, and that is going on even today when we talk of 18 nanometer, 14 nanometer MOS devices. So this is basically the roadmap of the VLSI technology across the years. It has started with the 0.25 micron technology way back in 1997 to 35 nanometer devices of today, or even as low as 10 nanometer, 14 nanometer devices, which are there in the research labs. So naturally, the next question is how is this miniaturization possible? If you look at the current equation of the MOS transistor, then it can be basically split into three terms: a function of technology, W/L ratio, and function of voltage. The trick is that you reduce L, reduce W, and keep the ratio the same. The functionality remains unchanged. And that's why a 50 micrometer by 10 micrometer MOS transistor is going to behave in the same way as a 5 micrometer by 1 micrometer MOS transistor. However, it's not so simple as a statement itself, because lots of issues come up as you keep on downsizing the transistors, and lots of weird things come up as you go to the nanoscale regime from the microscale regime. And there are obvious reasons why people have gone for MOS technology in lieu of the bipolar technology, which was very popular until the mid 90s or late 90s. That is because MOS transistor, this miniaturization is so easily possible by making use of the